Yeah, so I'm Florian. I'm a PhD student here at Texas A&M University Corpus Christi, working with Dr. Liu Chuntao as my PhD advisor. And I'm going just to present the stuff as you said, I presented at the AGU last year. It's a simple comparison between the Amazon and Central Africa, specifically Congo Basin, ice microphysics-wise. And all that is inferred from satellite observation. So I'm going to use both TRIM and GPM. We are going to take advantage of the precipitation radar and brightness temperatures from the radiometers. And I'll take advantage of the fact that TRIM has a LIS sensor as well to get some lightning information from that as well. As I said, I work for Chuntao. Let's say I work with Chuntao Liu. So I'm using his precipitation feature database. I'm more specifically going to use both TRIM and GPM database. That's two different data sets built either on TRIM or on GPM. I'm going to talk a lot about PFs and precipitation features. So what is that? It's simply just we take advantage of their KU band 13.6, 13.8 gigahertz frequencies since we have some kind of information about the surface precipitation. Whenever we do have at least 4 contiguous pixels of surface precipitation, we're going to draw an ellipse around it. And this ellipse is what we call this precipitation feature, this PF. And then Chuntao has done some kind of work with doing some collocation. We have GLM, we have all kind of data sets that you can dream of. We have ARE5 or all kind of cool stuff. So why did we pick the Amazon and the Congo Basin? Simply here on the top, I'm going to try to show it, if that makes sense. I've got here, I'm showing the precipitation features based on TRIM. So only the precipitation features that had lightning, since TRIM has the LIS sensor. I'm showing on panel A the distribution through the globe. And we can find the 3 lightning hotspots that are well known. We have South America, we have Central Africa, and we have maritime continents. Now, if we just keep this exact same map, I keep my precipitation features that do have lightning, and I do some kind of filtering to only keep the ones that had a maximum height of 30 dBz with a temperature lower than -10 degrees Celsius. We can see that the map is the same one, not much change. It's different maps, trust me on that. And this filtering comes from a paper from Chuntao from 2010, where he showed that approximately 10% of the PFs that have this 30 dBz at -10 have lightning over land, and over the ocean, it's at -17. Now, if instead of doing this filtering at 30 dBz at -10, we do a filtering at 40 dBz at -10, we can see that the map is really different. We kind of lost the Amazon, but we kept the Congo Basin, which tends to show us, since we are looking at radar data, it's a filtering on the radar data, that there's perhaps and probably a difference in the ice microphysics between the systems in the 2 regions. Now, if we keep in mind that radar reflectivity, is a function of both the number of hydrometers that you do have and their size to the 6th power. And we see that the Congo Basin is able from 30 dBz to reach 40 dBz, but the Amazon is kind of stuck and we lose a lot of features there. Perhaps basically just our hypothesis is, hey, maybe the radar reflectivity values in the Congo Basin are driven by the size to the 6th power, which easily gives us, allows us more to reach the 40 dBz as well at -10. But since it's much harder for the Amazon to reach this 40 dBz at -10, perhaps it is driven by the number of hydrometers instead. So basically the hypothesis is just, hey, perhaps the precipitation features in the Amazon are built around more numerous and smaller ice crystals. First comparison that we done, a simple CFAD, cumulative frequency by altitude diagram. On my y-axis, I've got my altitude, 40 beams of altitude, and on my x-axis, I've got the maximum of reflectivity, Amazon, Congo Basin, and we do directly the difference between the two as Amazon minus Congo Basin results. Note that this plot and the 2 next ones that I'm going to show you are all normalized level-wise on my y-axis. So they are normalized horizontally. I hope I didn't butcher this word. So if you just pick any level like 10 kilometers and you add up all the values from 10 kilometers, you're just going to add up to 100%. It just allows us to do some kind of analysis in the distributions, because what we want to compare, we just want to compare PFs that are in both areas, in the Amazon and the Congo Basin, with similar properties. Whenever we do look the difference between the two, we can see some kind of triple structure with the highest maximum of reflectivity, where the domination is from the Congo Basin, same thing for the lower values. And we have some kind of narrow distribution in red here that is dominated by the Amazon. So if we just go back to the hypothesis that we did, it kind of makes sense if we think about the fact that if this maximum of reflectivity is driven in Central Africa by either we do have this big stuff in the cloud or we do not have it, then it makes sense that we have a broader distribution in Central Africa. On the other side, if we consider that with our hypothesis, perhaps the reflectivity is more driven by not really the size, it will always be driven by the size, but more so by how much the content in smaller ice crystals in the Amazon, where then perhaps this more consistent and narrow distribution makes sense in this case. Next, we did a comparison with lightning. So I'm using trim again here because, well, only trim has lightning information. This is a plot that I really like. We got on the x-axis, we've got the flash count per PF. And on the top row, on the y-axis, we've got the total ice water content summed up through the entire PF. And on the bottom row, we've got the area of LBZ at minus 10 degrees Celsius that I'm just going to commonly call A charge because it's a good assessment of the size of the core. Again, we've got the Amazon, Congo Basin. We do the difference between the two. Again, it's normalized. So this difference is going to help us to, whenever we look at any value, to kind of see the switch in the distributions. And we got a black curve that I'm going to explain right after. So again, what we can see directly, and that kind of jumps to your eyes, is that for any value of either A charge or ice water content that you do pick, we can see that there's significantly, on average, significantly more lightning for two similar PFs in the Amazon and Congo Basin, significantly more lightning in Central Africa. As I said, we tried to quantify how much lightning difference that is, and that's the black curve that I have on the right. Simply doing the average flash count in the Amazon divided by the average flash count in the Congo Basin and shown as a percentage. I'm not showing values when it's too high or too low because it's just too noisy, not really trustworthy. What we can see is that when you have relatively lower values of ice water content or A charge, we've got some kind of ratio of 1. Basically, two similar PFs with lower values of ice water content or A charge are probably going to have on average a similar flash count in both areas. But as you increase this value, basically the amount of highs that you have in the cloud, you can see that we are shifting from a ratio of 1 to a ratio of approximately 0.5, even slightly lower here. Basically meaning that for two similar precipitation features, one in the Amazon and one in the Congo Basin, with relatively high amount of highs, you'll tend to have twice as much lightning on average in the Congo Basin. So that's quite a significant difference. Another way to quantify it, just in this table here, instead of looking per level, we're just merging everything. We look in the Amazon, we sum up all the flashes that occurred through all of our precipitation features. We divide it by either the sum of all the ice water content or all the A charge values. We do the same thing in the Congo Basin, and when you do the ratio of the two, you get 0.7 and 0.6. So again, that's quite a significant difference. So that basically does mean that whenever you do increase your ice water content, basically the ice content that you do have in the clouds is going to translate as a significant increase in the lightning in Central Africa, but this increase in lightning is not as significant in South America. And if we go back to how does lightning work, at least how does it start? It starts with interaction and shocks between the icy stuff in the cloud, more so between the big stuff, usually the graupel, and smaller ice crystals. And since we do know that at these temperatures, all the clouds will have the small stuff, it's basically a reaction that is limited by how much big hydrometeors you do have in your cloud. So whenever in the Congo Basin, whenever you increase your amount of ice, if it significantly increases your amount of lightning, that does mean that this increase in ice significantly increases your amount of big particles as well. But on the other side, in the Amazon, whenever you increase significantly your amount of ice, if it does not significantly, or at least not as significantly, because it's just a comparison, not as significantly as it would be in Central Africa, it doesn't mean that this ice, even if it obviously had to increase slightly as well, the amount of big stuff, it probably went somewhere else. And if it went somewhere else, well, we're expecting that it went towards smaller ice crystals. Next, we did a comparison with using brightness temperatures. Here, I'm only going to show GPM because we have more channels to work with, but we did it with trim as well, and we have similar results for the few channels that it has. Again, we're doing a comparison between the maximum height of solid dBz on the y-axis here, and on the x-axis, it's a minimum of brightness temperature, so one value per PF. Again, it's normalized horizontally, just to see a shift in the distributions. And I'm only going to show for each channel, 37, 89, 166 vertical and horizontal polarizations, and 183 plus minus 3 and plus minus 7. I'm only showing directly the difference between the Amazon and the Congo Basin. One thing here that could be problematic for some folks, I guess, we are doing some big assumptions. Because we do know that each of these frequencies are affected by a lot of processes, physical processes in the cloud. But there are some studies out there that tend to show that perhaps we can pinpoint, at least for each of them, some kind of main process that is driving it. If we're looking at 37, for instance, we have a paper from Don Cecil in 2009 that tends to show that it is probably mainly driven by large hail. And the other ones tend to be, for instance, 89, more icy stuff, ice water path, 166 probably frozen precipitations, and 183 probably ice and weather vapor. Again, we are looking at brightness temperature, so the lower the value, the more attenuation of the signal there was, and obviously the more, the stronger the physical process was. If we look at 37, again, we do have this kind of triple structure that kind of makes echo to what we had in the CFAD, where we have a much broader distribution of the values for Central Africa compared to the Amazon that has some kind of narrow distribution in the center. That would tend to show again that either you do have the big hydrometeors and then we do have very low brightness temperatures in Africa, Central Africa, or we don't, and we are somewhere in the middle, higher brightness temperatures. And in the Amazon on the opposite side, this narrow distribution tends to show us that perhaps the content in bigger stuff is definitely lower. When we do look on the other side at all the other channels, we can see that the lower brightness temperatures tend to be dominated quite heavily by the Amazon. So that kind of gives us the idea that in Central Africa, you would tend to have bigger particles, ice particles at least, but in the Amazon, you tend to have overall a larger amount of ice. So if you have more ice overall in the Amazon, but you have bigger stuff on average in Central Africa, that probably means that this ice had to go somewhere else. And if it went somewhere else, it probably went towards, again, smaller and more numerous ice crystals. And that's the quick summary of the thing. Basically, when you look at same altitude, Congo Basin tends to have much higher reflectivity values. When you look at the same ice water content or H charge, so again, area of 30 dBz at -10, Congo Basin tends to have significantly more lightning than the Amazon. And on the brightness temperature side, it tends to show that Congo Basin has larger stuff on average, at least it can go to the larger side, and the Amazon has more ice on average. So at least if I didn't convince you that perhaps precipitation features, thunderstorms, storms over the Amazon are built around smaller ice crystals, at least the data that we're using is definitely not rejecting this hypothesis. And that's it for that. I've got like 4 more minutes. I'll get some more goodies for you guys. This was basically just the basics of the work. We're doing a comparison between the Amazon and the Congo Basin to try to show, hey, perhaps we are built around smaller stuff in South America, sorry. But now we wanted to know, okay, we did this comparison with Central Africa, but what's the status of the Amazon compared to the rest of the world? So for that, we are using GPM, radiometer. So again, we are looking at the brightness temperatures. We have 37, 89, 166 horizontal and vertical polarizations again, and 183 plus minus 3 and plus minus 7. I'm going to go quickly over that to not go over time. We are not looking at all the precipitation features because, again, we want to compare what is comparable. So we are going to do a filtering to only look at the precipitation features that had the temperature at the maximum height of solid BZ between minus 17 and minus 10 degrees Celsius. Why? Because, again, it's coming from the paper from Chuntao in 2010. Basically, it means that we have approximately 10% of the PFs over land that have lightning and approximately 10% of the PFs over the ocean that have lightning as well. To do this comparison, we just, in each of our frequencies, in each of our channels, we look at the 15 by 15 degree box that we had for the Amazon, and we compute the median brightness temperature for each channel, and we compare it with the median brightness temperatures that we have in each 3 by 3 degree bin that we have through the entire domain, doing the local 3 by 3 minus the 15 by 15 Amazon box. Which means that everything that is warm colors means that on average, at least the median value tend to be higher than the Amazon, and everything that is like colder colors, blue, greenish, grayish, the Amazon was higher for the median value. What we can see, and we kind of go back to the idea of, hey, the Amazon is kind of a green ocean thing. We can see that the Amazon has a median, and this is consistent through all the channels, slightly different for 37, but I won't have time to talk about that, I think. The Amazon, at least the median value tends to be much lower, significantly lower than most land areas, but significantly higher than ocean areas. So again, we go back to this idea, hey, it's not really land, it's not really the ocean, but it's kind of in the middle somewhere. Now, if we kind of try to find what are the locations in the domains that looks like the Amazon the most, if that makes sense in English. So that would be the colors that are gray, grayish, really light green, a little bit of yellow on the positive side. We can find them, and it's quite consistent through all the 6 frequencies with the SPCZ for South Pacific Convergence Zone and kind of north, tropical north of the Pacific. Kind of with on the coast of India. These kind of areas tend to be the closest to what we have in the Amazon, that's consistent through all of the frequencies. And if I go back to the first figures that I showed you, that's where we find lightning over the oceans. So perhaps it's just a coincidence, perhaps it is not, but I think that's a cool thing to know, and we'll probably have to work more on this aspect. And that's basically it. The Amazon is not really land, it's not really the ocean, somewhere in the middle, and this middle we can find it in the ocean where we have lightning. So that's quite interesting. And I'm all done. That's it for me. Thank you for listening. If you have any questions, any suggestions, any comments, any feedback, we are always looking for this kind of stuff. Well, I'm still learning, so thank you.
That was awesome. Thank you, Florian.
Yeah,
I really
thanks.
liked your summary slides in particular. So everyone hang on to your questions. We'll have them after Kenza speaks, but I know I already have a few. Okay, next we'll have Kenza pull up her slides. So Kenza Tazi is currently a PhD student in her final year at the AI for Environmental Risk doctoral program at the University of Cambridge and the British Antarctic Survey. And before attending Cambridge, she, like Florian, earned her master's degree in physics, but she attended the Imperial College London. And Kenza has extensive experience training and applying machine learning models to a variety of different environmental processes and risks, which I think is really interesting, including everything from wildfire forecasting and cloud identification to her precipitation prediction work, which is what she will be talking about today. So I will hand it over to Kenza now.
Great. Can you hear me? Can you see the slides? Awesome. So good morning or good afternoon. So today I'll be presenting an extended version of my AGU talk from last December. More specifically, I want to discuss a new framework for assessing the likelihoods of extreme precipitation events under different climate scenarios over high mountain Asia. This work is still very much in progress, but it's made it this far thanks to the support of my advisors, so Scott Hosking, Andrew Orr, and Richard Turner. I'll start by introducing high mountain Asia and why precipitation is important, but a challenging thing to model in this area. I'll then outline the aims of the project before giving an overview of the methodology. And finally, we'll look at some preliminary results before discussing some avenues of future research. Okay. So high mountain Asia is the high altitude area of the Asian continent that includes the Hindu Kush Mountains, the Himalayas here, and the Tibetan Plateau. Most of Asia's great rivers, such as the Indus, the Ganges, and the Mekong, originate from these mountains. And together they work as a water tower, storing snow and ice in the winter, which melts in the spring and summer. So through this mechanism, high mountain Asia supports the livelihood of over 1.9 billion people by providing fresh water for domestic use, agriculture, industry, and energy through hydropower plants. However, in the face of climate change and increasing water demands, the water security of this area is under threat. And the biggest uncertainty for future hydrological modeling, including extreme events such as floods, landslides, and droughts, is precipitation. Precipitation in high mountain Asia is relatively poorly constrained, and this is due to several factors, including complex topography, limited direct measurements and access to those measurements. But the end result is that regional climate models, or RCMs, the principal tool that is used to make future precipitation predictions in this area, are relatively inaccurate. And it's not uncommon to get errors of order of 100%, even for seasonal averages. That's not to say that these models are useless. We know, in fact, that combining multiple climate models together can improve prediction accuracy, but there's little consensus on the best way of doing this. So for this project, I'm looking to aggregate the outputs of the coordinated regional downscaling experiment for South Asia, so the South Asia domain, which is Cordex WAS for short. So Cordex is an experiment that dynamically downscales climate simulations from global climate models in the Climate Model Intercomparison Project, or CMIP, to provide high-resolution climate data for regional and local applications. So Cordex South Asia is a 13-member ensemble that uses 3 RCMs driven with 10 CMIP5 global climate models. And they downscale these global climate models following a rigorous experimental protocol that allows for a straightforward comparison between the different regional climate model outputs. Because these climate models are free running, we can't just compare them like for like, so at each of the same times and locations. We have to do some aggregation of the data so that it's consistent over a climatological period. So here we're going to be aggregating the average monthly precipitation data month by month over a 30-year period. So in this project, which we've named Beijing Committee Machines for Regional Climate Models, or BCM for short, we're proposing a probabilistic machine learning framework to combine the 13 RCMs from the South Asia Cordex. And the framework, although it is for Cordex, it could be applied to any ensemble of regional climate models. So more specifically, the aims here are to combine the models in the RCM ensemble in a way that improves the accuracy over just taking the arithmetic mean, that allows us to draw samples from the model that are representative of future predictions. The model should also allow us to quantify the probability of extreme events for a given time or location, and make these predictions at arbitrary locations, not just necessarily where the model is being trained. And finally, and most importantly, we want to leverage the heterogeneous biases that exist in the RCMs over time and space. So to do this, we're going to have a two-step approach. First, we're going to model the RCM outputs across time and space in a probabilistic way. And then second, we're going to aggregate the predictions across the RCMs. So let's have a closer look at the first step, where we want to design a model that can make probabilistic predictions from RCM data. And we can do this with Gaussian processes, which are a type of machine learning method similar to kriging, if you've ever heard of that before. So a Gaussian process, instead of outputting a single scalar value, like this one, it's going to output a probability distribution for every time and location. And over a large number of inputs, we can see these as distributions over functions rather than points. And that means we can sample realistic trajectories of precipitation across time and space, like this. So more formally, we're going to say that, it's just a little bit of math, I promise there won't be any more, that an RCM output, yi, for a given month and location xi can be modeled with a function f, plus some noise, eta, I, which we're going to assume is normally distributed. So this function f, it can be modeled by a Gaussian process, which again, more formally, you can define as a stochastic process where any finite collection of its random variables, so the y's, are just a multivariate normal distribution. And just like a multivariate normal distribution, it's going to be defined by a mean function mu and a covariance function k. And here the x's, they're just showing arbitrary locations that you could have in your data. So for example, the k function that represents the covariance is just modeling the correlation of the, for example, our precipitation value at x prime with respect to x. So one of the key properties of Gaussian processes is that we can use the variance that they're outputting from these distributions as a way of representing uncertainty. So here on the right, we have a plot that shows the typical output of a Gaussian process. Here, a Gaussian process has been fit to these observations in the blue dots. And the black line represents the mean of the distributions that the Gaussian process is outputting. And the shaded blue regions, the distribution's 95% confidence interval. And we can also sample from the model to find possible functions that could fit the data. And these are shown in these dashed lines. The point that I want to make with this plot is that the GP variance is very small next to the data points. But when it gets further away from them, the distribution gets larger and the variance increases. And the model is said to have like more uncertainty in these locations. So summarizing the slide, because it's pretty important, the GP outputs Gaussian distributions. These distributions are defined by a mean and a covariance function. And the variance of the output can be used as a way to quantify the model's uncertainty. So I'm now going to talk about, I guess, the three main contributions I'm making on the methodological side of this project, which are going to change the original GP definition as I've presented it here in order to model RCMs effectively. The first change we need to make is warping. So although we're working with monthly precipitation data, the probability distribution that we're getting from the RCMs is not going to be normal. And to get around this, we can warp or transform the inputs and the outputs of the Gaussian process model. So here we have a diagram illustrating this. On the top row, we have the data in the form of a time series. And on the bottom row, we have its corresponding empirical probability distribution. So in step one, we're going from the raw data and transforming it, in this case with the Box-Cox transformation to make it look more Gaussian or normal. We're then going to fit a Gaussian process to this transform data. And then in step three, we'll take the inverse transform of the outputs to recover a probability distribution that's quite similar to the original data, and then also have calibrated uncertainty estimates. The second issue we need to deal with is that the variability we get from month to month within the RCM is not uncertainty, but it's actually intrinsic climate variability, which we don't want to minimize. So for this reason, we're going to model mean precipitation and intrinsic variance as two separate targets or parameters using a chained Gaussian process. So in this case, the mean and the covariance of the function f of the GP that we saw earlier is going to be represented by a function f1 for the mean and a function f2 for the covariance, and f1 and f2 are themselves Gaussian processes. So this is really important as well, because this formulation actually allows us to have heterogeneous variance at the locations where we have the data. And this is what I'm showing in this plot on the right, where again, the blue dots, they represent the data or the outputs from one of the RCMs as a function of the months of the year. And we can see again, this black line, which represents the mean of the distributions that the Gaussian process is outputting. And then the shaded blue is the variance or the confidence interval for one standard deviation, then in the light blue, 2 standard deviations. So the third and final issue with using an exact GP, as people like to call them, is that this method scales pretty poorly with a large number of data points. And to overcome this issue, we can combine Gaussian process models together using a Bayesian committee machine. So I'm going to give a high-level explanation of how this works. So let's consider some data on an XY plane. What we're going to do in a first instance is divide the data into different groups or domains, and then we'll fit a Gaussian process to each of these. We now want to know what the value is at this location, this orange location, and we'll ask each GP to give a prediction at this location. But as we remember from a couple of slides ago, the uncertainty of the GP that's very far away is going to be very high if we're trying to predict at this location that's far away from the training data that the GP has seen. And conversely, the uncertainty of the GP that's been trained close to this data point is going to be fairly low. So the Bayesian committee machine will use the variance of the different GPs to downweigh the GPs that are further away from the orange point and upweigh the GPs that are close to it. So this method is really neat. It allows us to conserve all the attractive properties of Gaussian processes while speeding up inference. And so the Bayesian committee machines are really what is underpinning this framework and making it viable to apply across a period that's as long and a domain, an area as big as high mountain Asia. Okay, so bringing this back into the context of modeling RCMs, we're going to start with our South Asia Cortex ensemble. We're going to take each output or the output of each RCM and then divide that into n manageable spatial temporal domains D, and then we'll fit a warp/chained Gaussian process to each of the domains before bringing them together with a Bayesian committee machine. We can then combine the Bayesian committee machines together to generate a model that draws on the information of all the ensemble members, and this represents the second step in our framework. So to aggregate our predictions across RCMs, we're going to use historical precipitation to weigh the Bayesian committee machine outputs. And to do this, I'm going to introduce a few statistical concepts. The first is going to be a mixture of experts, which is simply a weighted sum of probability distributions that we are getting from the Bayesian committee machines. So to determine the weights of the sum beta j, we're going to compare the historical RCM outputs from the Bayesian committee machine for each location and month with that of a reference historical data set over a 30-year period. And in this case, we'll be using Aphrodite. This is a data set that is generated by interpolating gauge data, so from weather stations onto a grid using a custom-made lookup table. And it's really considered the gold standard for precipitation across monsoon Asia and the Himalayas. Before we go ahead and calculate the weights, we first want to make sure that we are focusing on choosing models that do a good job representing precipitation extremes. This means we should look at the overall shape of the distribution rather than the absolute values. So we're going to scale the outputs by the 95th percentile before doing this comparison. And we're also doing this because we're interested more in the fractional rather than the absolute changes between predictions. And actually, it's been shown that looking at the fractional change is a more accurate way of assessing climate models for future predictions. And then the weights are going to be calculated with what's known as the Wasserstein distance. So that is going to be the distance that comes, or as a way of, measuring the distance between two probability distributions, our RCM outputs, and our reference dataset distribution. So the Wasserstein distance, it comes from optimal transport theory, and you can basically see it as calculating the cost of moving a pile of dirt. So for example, in the shape of this blue probability distribution, into some holes in the ground that would be the shape of this purple distribution, for example. So now let's move on to some initial results. We can first look at the typical output for a Bayesian committee machine. So here in the top row, we have the model's mean posterior distribution. So this is just the distribution, as I mentioned before, of the Bayesian committee machine, but once it's been updated with the data or fit to the data. And we're plotting the output here for both the monsoon time and winter time. Here, lighter values represent higher precipitation rates. And on the second row, we have the model's 95% confidence interval. And again, lighter values here correspond to higher precipitation rates. We can also visualize the Wasserstein distances between Aphrodite and the historical RCM predictions. So in the first row, we have the Wasserstein distance as a function of the month of the year for a specific location. Higher values mean that Aphrodite and the Bayesian committee machine outputs have a larger difference between the distributions. So for this location, which corresponds to precipitation in the Karakoram Mountains, the distribution is most different during the winter time, which corresponds to when most of the precipitation is being deposited during the Western fronts. And then we can also visualize the distances over space for a given time. So here we're looking at June over a small region. And here again, lighter values correspond to higher Wasserstein distances or larger Wasserstein distances. So if we take the RCMs with the smallest Wasserstein distance, we can actually create a neat map of which RCM is most accurate for any given location and month of the year. And this is exactly what I'm plotting here. So here, each of the RCMs that I have, this is only for 5, is represented in a different color. And we can really see that different RCMs perform better at different times and different locations across high mountain Asia. So for example, in December, the NOAA-driven RCA4 regional climate model is really dominating over high mountain Asia, for example. And this is not just like a random pattern. There's some structure here, which is quite interesting. So we can then apply the weights that we got during the historical reference period and plot the outputs. Plot the outputs for future predictions. And so here I'm showing far future predictions between 2066 and 2095 for RCP 4.5 and RCP 8.5. So in the first column, again, we have outputs for the monsoon season and then winter time. Here, darker colors represent higher precipitation values. And the dotted areas show the areas in the study area where the outputs are below the weighted historical 5% percentile, And the hashed areas show the locations where we have areas above the historical 95th percentile. So with the caveat, we're only using 5 RCMs for these plots. I'm going to make some observations, which I found interesting. The first is that we can see that under RCP 4.5, precipitation decreases over the Tibetan Plateau, but increases over the Hindu Kush Karakoram during the winter time. RCP 8.5 is characterized by a strong intensification of precipitation in the eastern Himalayas during the monsoon, but also a healthy increase in precipitation deposits in the Hindu Kush Karakoram region during the winter time. Although I haven't made any formal analysis of these plots yet, the initial results are pointing towards extremes being probably underestimated over high mountain Asia compared to previous research. Okay, so today we've seen that we can use Bayesian committee machine and Bayesian committee machine framework as a way of aggregating climate models in a probabilistic way. The main contributions on the methodological side were creating a method that simultaneously deals with non-Gaussian distributions, creates heterogeneous variance, and is scalable to larger data sets. Our initial results show that different RCMs perform better at different times and locations, which we were expecting. And probably future extremes might be underestimated over high mountain Asia. But there's still a lot of work that I want to do to consolidate all the initial results I've shown so far. First of all, we want to start by including all 13 of our Codex South Asia models. There also needs to be a more in-depth comparison and analysis of extreme representation on a held out reference period. So the one that we haven't used to calculate the weights, and also like doing a proper comparison with the arithmetic average. Also want to repeat the analysis that I've done for not only monthly precipitation values, but also for consecutive dry days and wet days. On the machine learning side, it would be nice to jointly model the weights and the outputs from the Bayesian committee machines together, rather than just sampling my mixture of experts. And finally, hopefully your suggestions. As I said, this work is really still in progress, so I'm very much looking forward to your feedback, and I'm of course happy to take any questions. Thank you.
That was awesome. Thank you, Kenza. Okay, now we can go into the discussion section of this seminar. So if anyone has questions, feel free to put them in the chat, raise your hand, or at this point, probably just unmute and ask them. Yeah, take it away.
Okay, yeah. So a question for Florian, which is, you looked at the microwave brightness temperature, and we know that, you know, the passive microwave brightness temperatures are used for precipitation retrievals, and the retrieval schemes that we use, which is GPROF, is known to have opposite biases between Africa and South America, which is typically attributed to convective organization and stuff like that. Do you know what the impact is with regards to the ice content and the differences on the precipitation retrievals, whether it can explain the biases?
Wow, I didn't expect that. I've never heard about that, so we don't really look into it. We really just look at the precipitation feature side and just look at what the differences were. I don't know there were such a bias, but that's interesting, and that does mean I have to check it now.
Well, it's biased on
sure.
the precipitation retrievals. So from the brightness temperature to millimeter per hour rain.
Okay, so that could mean that I guess we could oversample on the precipitation features number. But after that, the other what I mean is that the other parameters should be the same, so we shouldn't have any issue on this side. But I don't know much more about that. Sorry.
Okay, I'll post the paper I was thinking of in the chat.
Yeah, please. Thanks.
No one else is going to jump in. I have a question for Kenza. So I think your approach with like the Bayesian committee machines is really clever, because so many people, I think, struggle with how to evaluate such a large amount of data. First, you have the dimensions of GCMs. Then once you start regional climate modeling, then you get the dimension of like different RCMs and stuff. And I guess I was curious, you seemed to mention a little bit about internal variability when you were talking about keeping that in and not correcting everything to like a mean state and stuff. And I guess I was curious if you have a feel yet for how much internal variability is playing a role in this uncertainty. If you like thought about basically doing the analysis you did, but removing kind of that part where you modeled the internal variability separately and seeing how much that changed your evaluation of RCMs. Because I think a lot of people, when they evaluate, will pick one that matches observations really well and not realize it's just, you know, one member of that whole GCM ensemble and presenting one possible way the climate could look. And then they say, you know, this RCM did best or this GCM did best, but it's just one member. So that question kind of wandered, but yeah, I guess I was curious if you had a feel for how important that step was, where you decided to model internal variability separate from the mean state.
I think it's really important. So when I was showing my slide, I was showing the observation on the transform data, which is going to look a lot more normal than it would once I did the inverse transform. But hopefully the way that when I'm doing the weighting of the different models, it should be looking at the whole probability distribution, not necessarily just the mean. So if the probability distribution is very skewed compared to the reference, that would downweigh it quite harshly. So my sense is yes, like if the variance is quite different, then the model is going to be weighted quite heavily against, or like down weighted for that. Does that make sense? But I'm really interested in looking at the whole shape of the distribution, not just looking at the mean or taking the variance, because again, we're looking at heavy tail distribution. So that's not necessarily a good way of summarizing the distribution, if that makes sense.
No, that makes a lot of sense. I think most of the Cortex results I've seen have been from the US, where you don't have such a heavy tail distribution, especially in the Southwest. Go ahead, Jackson.
Yep, it's me again. And now for Kenza, a question. So you're choosing, a high mountain Asia region, which is of course very important, but it's also a very challenging area to study. And you use Aphrodite, which is a good data set, but people would say, oh well, how reliable it is. Have you considered applying your entire method in a region where we have very good ground observations or even reliable future projections, like maybe the Europe area or the US area? So you can sort of demonstrate the value of this approach before you apply it to high mountain Asia region.
That's a really good point. So I've done that. So my PhD has mostly been about Bayesian machine learning applied to high mountain Asia. But in my previous projects, I have done this comparison where I've looked at Europe first, and then I've then applied it to high mountain Asia. And I said, okay, look, the results are worse in high mountain Asia, but it's because it's just a lot harder to model the precipitation there. So yeah, that would definitely be something useful to do, I think. I think people don't understand exactly how bad like the data disparity is between these regions that are well studied and regions that are not.
Okay, right, thanks.
So this is from Lisa Milani, and she asks Florian, have you tried the global comparison also with respect to the Congo Basin, and does it have similar areas around the world as well, possibly more on land in this case, rather than?
No, we did not, because obviously we are focusing more on the Amazon because that's also the area of interest here. But yeah, we can definitely expect that we would have probably some areas of relatively higher lightning activity that would be really comparable to what we saw in Central Africa. Yeah, from what I remember on the maps, most of land at pretty much pretty close median brightness temperature values. I would have to check it more in detail because of the color gradient that was not perfect to do this comparison. Yeah, I could take it a look and get back to you if you want.
We have a question from
yeah, I have a question for Florian. So one of my colleagues found there's a relationship between humidity and lightning. And you kind of touched on the humidity a little bit. And what's your thoughts on the relationship between humidity and lightning? Is there a huge correlation or not? Have you looked into those?
We didn't really look at humidity directly. There is probably a link with lightning because, well, the microphysics of lightning is quite heavy, and a lot of things are happening in that. So perhaps it is playing a role, but we have to keep in mind as well that Congo Basin is a place that is quite similar to Amazon. It's not a dry place at all. It's pretty wet as well, so we can expect it to be quite humid as well, quite comparable to the Amazon. I didn't really directly looked at it, but I can at least expect the conditions to be quite similar.
Yeah, thanks.
I think we have time for one more question if anyone wants to slide in. Okay, I'm going to take it. Kenza, I was curious if you guys are working with any sort of stakeholder entity or anything, because I feel like a lot of times the way these RCM results are interpreted is, I think, very subjective, depending on like who's looking at it. If it's like a government entity, or like here in the United States, a lot of the people who care about it are like from the Department of Energy or Department of Defense. And so I was just curious, I guess, what the stakeholders in this region might look like, and if you guys have thought about that side of like how this would help them make decisions, or help anyone make decisions, I guess, about that area under a future of climate change.
Yeah, that's a really good question. I think unfortunately, no, I'm not directly in touch with any stakeholders for this particular project, but it's definitely something I would like to do in the future. Yeah, generally, I guess like generally, I have spoken to stakeholders in this area through different consortiums like ICMod and the Himalayan University Consortium about data needs and what would be good to have in general. But I agree that having stakeholders be really closely involved at the project, and especially at the beginning, would be really useful and something I definitely would want to consider for my future work.
Thanks. Yeah, I mean, I assume that's part of why you guys are including like that extreme precip like consideration and kind of prioritizing that. Because that's really important. Okay, I think that brings us to the end of our very first 2024 seminar for the ECSPrecip committee. Yunjin, do you want to close us out?
Oh, go ahead, Sam.
Oh, okay. Awesome. I was just going to say thanks for joining us. Thank you so much, Florian and Kenza, for great presentations. All of your graphics and everything were phenomenal, which is obviously why you guys won this award in the first place. But yeah, hopefully we'll see everyone at the next seminar, which will include other student award winners, and will hopefully be in the next month or two.
Thanks.
Thanks, everyone.
everyone.
Bye.
Thank you, everyone. Thank you.